Hi everyone, my name is Evie, and today I'll be talking about processing methods for large-scale production of semiconductor quantum dots. So first, let's talk about some traditional methods for quantum dot synthesis. Quantum dots are very tiny particles around nanometer scale that are usually suspended in a colloidal suspension and that exhibit wide bandgap tunability because of their small size. There is a wide variety of quantum dots, including lead selenide telluride, lead sulfide, cad zinc telluride, cad selenide, even InGaAs, zinc oxide, all kinds of different metal organic quantum dots. And so they exhibit a large variety of processing mechanisms. The most common type of processing mechanism is the hot injection mechanism, or the rapid injection of organometallic precursors into a batch reactor, which is what we also discussed in class. A batch reactor is this 3-inlet flask, which you can see at the right-hand corner of my slide, where the precursors are rapidly injected in order to cause a solution to supersaturate. When a solution supersaturates, this causes instantaneous nanocrystal nucleation, which aids in monodispersity, which means we end up having a uniform size of nanocrystals, which is obviously highly desirable in order to control the band gap of these colloidal suspensions. The temperature then controls the growth rate, and so the size is still controlled, and the important process parameters here are injection speed, stirring rate, and bath temperature. However, even though this type of lab-scale synthesis method is widely used, it actually exhibits really low batch-to-batch reproducibility due to the reaction temperature that occurs right after this rapid hot injection. The yield is also really low at about micrograms per hour, and all of these precursors used to form these metal organic quantum dots are extremely hazardous, and so using them at a large volume would pose a lot of risks to the environment and complications in regards to neutralizing and disposing of these precursors. People have tried to combat this by using aqueous synthesis, and so having water as a solvent, but this leads to pretty poor quality quantum dots, and they've also tried to utilize microfluidics to control the temperature much more carefully, but this also lends to really low yield due to the fact that there are microfluidic channels. So in order to have larger volumes, we need to define some new process parameters, including mass transport, energy and heat transport, and momentum transport that will be essential in optimizing in large-scale processing. In order to have mass production, we also need to have high reproducibility, low cost, and have an environmentally friendly procedure. The first type of large-scale production mechanism that I'll be presenting is the continuous flow reactor. So while batch reactors only go through one round of synthesis, Kawa et al. Designed continuous synthesis from a continuous flow of precursors in the mechanism shown here on the right. B1 and B2 are feeding pumps for the feeding pipes C1 and C2, which each individually hold the solvent and the quantum dot precursor. C1 and C2 then flow into this reactor D, where the precursors are allowed to react. Then they move on to this maturing zone or heating zone E, where the nanocrystals nucleate and grow. Next, once the nanocrystals have nucleated and grown, they flow through a condenser and cool, and then are eventually collected in this collection bottle G. And precursors are continuously flowed through this process, so we don't just have one injection step. This increases the yield a lot to about 13 grams per hour. However, in this study, the reactor was only run for 1 hour. The capping organic reagent and high temperature reaction solvent was triactylphosphine oxide, or TOPO, as well as a cad selenium precursor. The static mixer also enhances mixing of starting precursors in this reactor. The process parameters that are important here are reaction temperature, choice of precursor, volume ratio of precursors, flow rate of the two liquids, which is determined by the pump pressure, as well as the cooling and preheating temperatures. However, the limitation to this continuous flow reactor is that hazardous solvents are still used, and if we were to scale this up, those large volumes of hazardous solvents would prove really difficult in disposing of. The next kind of large-scale synthesis model is the high-gravity synthesis, or high-G. This utilizes a rotating packed bed, or RPB, which is used to split aqueous reactants into micro or nano droplets. So because there's this rotating packed bed, which is rotating at really high velocities, this creates is essentially a higher than gravity force in the reactor, which intensifies mass transfer and micromixing by a lot. The gravity in this reactor is at 76 G, which is huge. The liquid slurry is introduced into the eye space of the reactor and then flows radially under a centrifugal force. There's a high degree of supersaturation throughout the reactor and homogeneous nucleation because of the micromixing that's occurring throughout the precursors. When there's homogeneous nucleation, the nucleation rate is highly dependent on the supersaturation concentration of the product. The liquid is also continuously pumped out of this stirring tank here and out through the pump and back into the high G reactor until the pH desired for the solution is reached, and the researchers knew that the quantum dots precipitated out fully. The process parameters that are important here are initial concentration of precursors, gas flow rate, and the slurry flow rate, as well as the rotating speed of the reactor. The limitation to this method is that you would need a really, really large motor, a really large chamber in order to scale this up, which is both high energy and high cost. Even though this is a great idea in principle, in practice for scaling up, it may not be so easy. The last method of large-scale processing that I'm going to talk about is called thermospray synthesis, in which aqueous or organic solutions of semiconductor salts are sprayed into monodispersed droplets. The solvent then evaporates from these droplets, and we're left with suspended nanocrystals that don't need any capping of any sort. First, we start off by dissolving the semiconductor powder in any solvent you choose. Next, liquid is pumped through a capillary tube with an HPLC pump, and a heating power supply is also attached to the capillary in order to heat this liquid. The liquid then passes through a T, which also supplies nitrogen flow to then form the droplets in this nebulizer, which essentially sprays out droplets of a particular size. Then the droplets pass through an oven, which heats the air through which they pass and causes the solvent in the droplets to evaporate. Supersaturation is then reached upon evaporation of the solvent, and the nanocrystals precipitate out. And we're left with nanocrystals suspended in air until they eventually reach a solid support or a substrate at the end of the oven. The process parameters that are important for this method are oven temperature, semiconductor salt concentration, and the current delivered to the capillary, which dictates the solvent temperature and liquid flow rate, which is very important for how the droplets form and the size of the droplets form at. The nebulizing gas flow rate and temperature are also important. The controls that we have are the outlet shape and the location of the nebulizer outlet relative to the capillary. So this process is very promising for scaling up to even larger degrees of synthesis because of its ease of integration. All you need is this nebulizer, and then you can build a huge oven as well as use any solvent of your choice. And so it's very environmentally friendly in that way. The droplet size is determined from this equation from Korpchak and Wynne, and depends on the surface tension of the liquid as well as the density of the liquid and the velocity of the liquid, as well as the concentration and flow of volume flow rate of liquid and gas. From the droplet diameter, we can calculate the droplet volume, and I've assumed that the droplet is made up of a piece of semiconductor precipitate and a surrounding area of solvent. This is obviously a simplified model, and in solution, the semiconductor precursor would be much more dispersed, but ultimately I'm choosing to model them both as spheres. The droplet mass is then given by this equation here, and we can use the concentration that we know of the solvent in the solute to determine the particle size from the droplet size. Next, in order to optimize the processing parameters, we can use Clausius-Clapeyron, a little bit of thermodynamics, to determine the vapor pressure of the solvent by knowing the boiling point as well as the heat of vaporization, which are both very well known for a variety of solvents. The evaporation rate can then be determined from the Langmuir equation, and we can use this to determine the ideal temperature in the chamber to ensure we have a high enough evaporation rate that by the time the particles reach the substrate, most of the solvent or all of the solvent has evaporated out. You could do this empirically by setting a really high temperature, but it's good to model in order to know how much energy you could save, how low the temperature could be, as well as the mechanism behind this process. So next, I calculated, or I show an equation for a drag force, which is calculated from the concentration of solute as well as the particle diameter and the velocity of the particle and the fluid surrounding it. And by equating this drag force to 1/2 mv squared, we can calculate the velocity of the particle and plug everything back in to be able to get our ideal process parameters of temperature. So by using ThermoSpray, we can achieve low-cost integration, freedom of solvent choice, and reproducibility with precise control of temperature and concentration, which makes large-scale production possible for quantum dots. Thank you very much.